Next speaker is Dr. Greta Assmann from the Paul Scherrer Institute, who was previously at University of Constance, and I think may show up there in the abstract, working with Kydritrix, but is now at the MX group at the PSI. And she's going to talk to us about the endlessly tricky but fascinating and extremely important subject of the statistics we use to assess and compare the quality of our data. Thank you, Greta.
Thank you for the nice introduction, and thank you for having me. As we can see, I will talk about data quality indicators, and I was asked to give an educational introduction, so I guess it's very relevant for all the students here. And I will start with the small content overview. So I will have a small introduction and then cover some data quality indicators that I think are useful for, as Graeme already said, for crystallography. Obviously, I cannot cover everything. And then I will go to my second part and talk about a bit about rejection approaches for rejection of bad data sets. So the first question I would like to answer is a bit like, what can we actually get? What kind of information can we actually get from our data in terms of data quality? I mean, the previous talk already touched this a bit, so I will talk about a little bit about accuracy and precision. So accuracy is basically, if you have a look at the right picture, you can see that accuracy kind of gives us how different our measurements actually are from the truth. In comparison to that, we have the precision, which kind of tells us how internally consistent the measurements are. And from that, we can see that accuracy is limited by precision, if you have a look at the picture. But high precision does not necessarily mean that we actually are close to the truth, so that we also have a high accuracy. So I think it's really important to understand that. And now, in our previous talk, Graeme was talking about uncertainties or errors. Sorry, I call it errors, but I want to relate this accuracy and precision problem to our errors that we actually have in the data set. So as I said before, if we have one case where accuracy is equals our precision, this is only valid if our uncertainties or errors are only random. So if no systematic errors exist. So this means that, as Graeme said before, if we average over several measurements, this error is reduced and we can actually estimate the truth. This means that data are isomorphous. The other problem would be if accuracy is not equaling precision. That means that systematic errors exist. And this is the case if we have systematic differences that are not reduced during averaging. And this kind of hides the truth. So in this case, we have data sets that are non-isomorphous. So the take-home message from this slide is that if we actually want to measure accuracy, which is what we want to do because we want to know how far away our measurements actually are from the truth, we cannot measure this because we don't have the truth, but so that we can only measure the precision that we have from our measurements. So if we do this, we still don't know if this is actually correct, only if we then solve the structure eventually. So I talked about systematic and random uncertainties or errors. And now the question is, coming to my first part of my talk, how do we actually calculate this precision? So there are several statistical measures to calculate precision. And I will start with R factors for unmerged data. So one famous one is R merge, which kind of gives us the relative absolute deviation of the intensity measurements from their mean. So this gives us, again, the precision. But the problem is that R factors or R merge, especially over 8, estimates the precision for low multiplicity data. So if you measure a crystal not that many times, so you have low multiplicity, then you get a higher precision, which is obviously not correct because we want to have several measurements to average the random error or uncertainties. So there was a new formula introduced that is called R-MEES, which corrects for this overestimation. And this one also has the problem that we don't have an upper limit. So this is the case for both of these indicators. So it's sometimes difficult to interpret. So if you have a very high R values, especially in the high resolution shell, it can get difficult to estimate. For example, if you want to do a high resolution cutoff for your data, it can be really difficult. Also, it's only useful to compare unmerged data. So if you want to go downstream the processing line, if you do want a structure solution or these things, you want to have a look at your merged data and not your unmerged data. So if we have a look at R factors for merged data, we have RPIM, which has an additional correction factor that accounts for the increase in precision by merging several independent measurements. But again, we have the problem that this R factor also has no upper limit. So there's another quantity that is called I over sigma. And this quantity has the problem that it suffers from variations in calculation due to different software programs, processing programs. And it will always rise when you merge additional data into it, no matter if the data are isomorphous or non-isomorphous, so kind of bad or good. So the take-home message from this slide would be, if there's, again, we have no upper limit problem for R factors, and also it rises with more observations, I over sigma. So obviously I will come to CC half, which I worked in my PhD a lot on. It's also a quality indicator for merged data. And it's derived from the correlation coefficient, so from mainstream statistics. And it's kind of well known. So you can also do significance testing for CC. And from this correlation coefficient, you can derive a quantity called CC half, which basically means that you split your data set into two halves and then calculate the correlation coefficient from one half to another. So this will again give us only the precision of the data, but it's a little bit easier to interpret. As I said, you can use significance testing. It only improves if you merge isomorphous data, and it will decrease, for example, if you include data sets that have radiation damage. So the question now is, if we have all these data quality indicators, how do we actually then relate this to our model quality? And the most famous, I would say, model quality indicators are work and are free. I think everybody knows this. There's an alternative to that, which is called CC work and CC free, which is basically the same, just calculated with the correlation coefficient. And I'm telling this because there's another quantity called CC star, which can be derived from CC half, which tells us the predicted maximum possible agreement between data and the truth. So it's kind of a theoretical value that tells us how good our data actually are or can be. And this allows us to directly compare data and model quality by using CC work and CC free, because these should converge towards CC star if the model is complete. If you want to have more details on that, just have a look at the paper from Kapus and Diederichs in 2012. So to sum this up, I talked about R factors. They kind of have their use, but especially when we're talking about high resolution cutoffs, it's very difficult to interpret. Then we have I over sigma, which is always increasing when you're merging more and more data. And then we have CC half, which is kind of useful because you can relate model and data quality and also have well-known statistical properties. Just a quick reminder, as Graeme also said before, also obviously you're interested in your resolution and your completeness. So if you compare data sets with these quantities, obviously you have to make sure that you kind of check what your completeness is and that you compare them with the same resolution bins. So now I talked about non-isomorphous data sets and isomorphous data sets and uncertainties. So the question now is, how do we actually identify if these data sets are useful for us or not? I mean, it's maybe a bit tough to say useful, but if there are some uncertainties which we don't want to increase in our merging. So there are some general approaches for that. I cannot cover all of them, obviously, but just to give you a brief overview, there's the HCA method, which gives us dendrograms. You can see one example on the right-hand side, which kind of clusters or gives us these dendrograms according to distances of single data sets. And these distances are calculated by different metrics. One very famous one is blend, the program blend, and the unit cell variation, for example, is used as a metric to define how similar these data sets are. Another metric to do this is using the correlation of, obviously, the common intensities from two data sets. Another big approach used in a lot of publications is done by rejection of data sets according to a cutoff. For example, if a data set has a specific number that for I over sigma, or for the correlation coefficient of the intensities, or for example, also for Z, for the anomalous signal, then these data sets are rejected or kept for merging. We also have genetic algorithms. I'm not an expert on that, but just to briefly mention it, there's an optimization of different subsets of data sets, also according to different combination of all these statistical quantities that were mentioned before. And also, we have a combination of all these methods as found in several pipelines at several beamlines. If you're interested, please have a look. I just mentioned a few. I guess there are more and more, which combine these different methods to analyze what kind of data we want to reject or keep. So always keep in mind that, for example, unit cell constants are a necessary but not a sufficient condition. So this can help, but not necessarily. And also, with the cutoffs, you always have the problem that you don't know where to set the cutoff. So this is why I worked in my PhD on CC12 again, and had the idea to use CC12 as an optimization target to actually find out which data sets I want to reject. For this, I decided to calculate a quantity called delta CC12, which tells me the influence of one data set on the overall data set. To put this in a simple formula, I calculate delta CC12, which is calculated by the CC12 of all data sets minus the CC12 without the one single data set I'm interested in. So if this delta CC12 is then negative, I want to reject this data set because it's impairing the overall CC12. I can iteratively apply this. And also what you can take home from this method is we have a clear cutoff when we want to reject the data set or not. And also we optimize for CC12. And I could show in my paper that it enables structure solution for some data sets where I couldn't solve the structure before. Another method I worked on is called X-scale isocluster. This was also mentioned before in James' talk, and also it's used in, for example, Ambigator for resolving indexing ambiguities. So it's basically a program that separates data sets according to systematic differences in space. And it uses the correlation coefficient of these data sets. So if you look at the image on the right-hand side, you can see that the data sets are kind of assigned somewhere in space, and the length of the vector represents how much random uncertainties we have. And the difference in direction tells us how big the systematic difference of these data sets is. So just to sum this up, I think the visualization is really nice because you can easily see if some data sets fit to each other or not. For example, here, this is obviously an indexing issue, so this is super easy to see. And you can also use this if you don't have any indexing problems, but have different systematic uncertainties in your data sets. So the last part I would quickly like to touch SFX and SSX data. So for now, I was talking about zero synchrotron crystallography data, but rotational data, so still like rotational wedges. And now I would like to cover a bit the challenges of zero synchrotron crystallography and zero femtosecond crystallography, so where we have no rotation. I think Richard will give us a full talk about this problem, so we'll just briefly touch it. So you know from the setup that we don't have any rotation and we have random orientations of these data sets. Diffraction patterns. So as a challenge, I would thinking about the rejection methods I just showed, that as we have this very low number of reflections for one still, if we want to compare single stills, every still to each other, then obviously we have to have something to compare with. And for that, we need common reflections. But as we have random orientations, the number of common reflections for two stills is sometimes pretty low. And then obviously the correlations that we get are maybe not that, let's say, significant or difficult to interpret. On top of that, we have the partiality problem that was also already touched. So we don't really know or can really estimate if the intensities that we are actually using are correct. So then we again have the problem that the correlations are maybe false. As a last point, we have a very high number of data sets, up to 100,000 data sets. So if you want to compare every data set with another, you have obviously a computationally very expensive analysis, depending on what kind of algorithm you want to apply. Last point, again, is that we have so many crystals, we also can have so many different, let's say, systematic differences in there. So potentially, so it gets also hard to, find out what's useful to merge. Speaking of SFX, I have a last slide to Edward for my colleague John from PSI. He wants to. He's looking for users at the MX Crystallina station at the Swissfell. So if somebody is interested, please get in touch with John or talk to me later after the talk. And with this, I would like to thank you for listening and thanks for inviting me. And also a special thanks to Kai, who is not here today, but he taught me all of this. And thanks to the whole MX group at PSI.
Thank you very much, Greta, for a fascinating talk. Do we have any questions?
Thank you for a nice talk, Martin Molly. Speaking. I have two questions, please. You said that you can use delta CC1/2 for rejection of data sets, and in the case of serial data, we can consider every image like another like one data set. Is it possible to use that? And
So I thought about it, but I haven't tried it because I think from my experience so far, the contribution of a single data set, let's say we have 50,000 data sets, like shots. If you look at one data set, the contribution is so small that I think there wouldn't be any effect to see, but I haven't tried really with numbers. But,
and then please, I would have a bit practical question. Usually when I process diffraction data, like from usual rotation method, I have several different settings of the data processing. In the end, I look at the IOR sigma asymptotic and decide using this statistic. And do you have any advice that what more shall I check than this? Maybe there is something what I also should check.
So I think IOR sigma asymptotic is also a useful indicator, but I didn't cover it for time reasons because I had to make a decision what I would like to cover. But I think, as Graeme already said also before, you would have to check probably like you said you would use different parameters for the different data sets. If I
mean like one data set, but using different parameters, different geometries or different data range.
And then your question was at what statistics you would have to look at, or
maybe because I usually I usually see IOR sigma and then the
I think
the best I will get.
I
mean asymptotic one.
What I would do, I would have a look at obviously CC half, and then obviously check if you have it at the same resolution. bin to compare, right? And then also look at the other statistics and decide what you actually want to look for. And then, yeah.
Okay, thanks.
So does your data emerge and see what you get.
Thanks. Very nice talk. My name is Derek from SSRL. I had one question. Can you comment on the randomness associated with CC half when you're computing delta CC half?
So originally, it was designed that you would literally randomly divide the observations of every unique reflection. But in the meantime, there's a new method called the sigma tau method where we get rid of this randomness. So if you would really randomly divide all the observations for every reflection, you would have to calculate CC half several times in an average, I think, from my understanding. So we got this new way to calculate it. If you want to have a look, I can show you later. And then, yeah.
Thanks.
You're welcome.
Okay, we should move on in the interest of time.